Here's video 1 for the statics unit. Now, for this unit, the big ideas are 1 and 3. So, big idea 1 is that objects and systems have properties such as mass and charge, and that the systems may have internal structures. So, we're going to talk about systems. And then big idea 3 is that the interactions of an object with other objects can be described by forces. So, for this unit, the learning goals that I'm going to grade, I want you to be able to model the properties of a system based on its substructure. I want you to be able to analyze, to make claims, and solve problems using forces and diagrams, or using vectors mathematically. And then I want you to describe a force as an interaction between two objects, and I want you to be able to identify both of those objects for any force. All right, so first off, objects versus systems. And a system is a collection of objects. And what's kind of cool is that you're free to determine the boundary for that system. So as an example, we can take a look at the planets in a solar system. And we can see how the planets are interacting with each other or with their sun. Well, maybe instead of looking at the entire solar system, I would just rather look at a single planet with its moons. Or maybe I'm looking at a planet and a person standing on the planet, and the system is that person and the planet. So systems themselves have properties determined by the properties and the interactions of their atoms and molecular structures. Now, in this course, when the properties of those parts are not important, when we're modeling the behavior of some larger system, the system can be referred to as an object. And an example of this, if we're studying a car crash, we really don't care about all the individual atoms in each car, because the individual atoms of each car, it does not affect the collision at all. And there's other examples we can use as well. Okay, moving on. Forces. This is an interaction between two objects. And we can usually think of this interaction as a push or pull. There are 4 types of interactions. The weakest is gravity. And then up from that is the weak interaction, which it's kind of responsible for some forms of nuclear decay. And then there's the electromagnetic interaction, which is the second strongest, and that deals with electric charges and magnets. And then there's the strong force, which is the strongest in nature, and that's what holds the nucleus of an atom together. And so far, everything we study can be described by one of those 4 interactions. So, the way we detect a force is by its influence on the motion of an object. The unit of force is the Newton. And 1 Newton is equal to a kilogram multiplied by meter per second squared. And we're going to learn why that is in our next unit. Now, contact forces, this is if you touch something or push something or something pushes you. That results in the interaction of one object touching another, but it arises from the interaction from the interatomic electric forces. We're all surrounded by a layer of electrons because electrons are, the outermost part of an atom. And as those electrons repel other electrons, that gives us a contact force. Some of these other forces include tension, friction, normal, spring forces. These are all electromagnetic forces. but it's kind of hard to see that at times. Now, once we are able to identify the interaction, we can now start talking about diagrams and the way we can represent those interactions. So a diagram is a useful tool that lets us analyze forces acting on an object, or the forces acting in a system, or the forces acting on a system. So what we do is we represent forces with arrows, and that's because they're vectors. And a vector is something that has, magnitude and direction. Magnitude measures the strength, so how many newtons, and the direction is measured in angles. And when we draw a vector, we use an arrow. Now, obviously, where the arrow points is the direction, and then the length of the arrow represents the magnitude. So if I have a 20 Newton force, I may draw my arrow 20 centimeters long so that I can create a scale that says 1 centimeter equals so many newtons. Now, any kind of force exerted on an object is always due to the interaction of that object with another object. So let's take a look by looking at like a football flying through an air. So first off, we're going to make a force diagram. So the forces acting on this football. Well, the football will be interacting with the ground, or with the planet. So that means there is a gravitational force. And this is going to point from the center of mass of the football to the center of mass of the Earth. So basically, draw it vertically down. The next thing is it's flying through air, so this football will be interacting with the individual air molecules. Now those air molecules are hitting the front of the football, so that's where I'm going to start the force for this one. I'll use a different color. This has a special name. It's called the drag force, or just drag for short. And those are the only two forces acting on this football. Some people may think there's a force pushing it, but there isn't. There was originally when the football was in the person's hand, but once it left that person's hand, these are now the only two forces acting on the football. So the drag is trying to slow it down, and the gravity is trying to bring it back to Earth. Now this is a force diagram. When you make a force diagram, you always want to draw the forces where they originate. So gravity is always at the center of mass, and the drag is right where the air particles are going to hit the football. So this is a force diagram. I can now make a free body diagram. And I make it free of the object's body. So I'm going to represent the football as a dot. And I'm going to put a Cartesian coordinate system on it. So the gravity force would point straight down, and then this drag force and I try to draw it at the same angle and the same length, but artistry. But notice then that both of those forces originate at the center of the object. Both of these diagrams have their pros and cons, but basically, the force diagram, you want to draw the forces where they originate, and on the free body diagram, you want to put the forces originating at the center of the object. Now, let's think about the interactions. The gravity was the ball interacting with the Earth. And the contact force, or the drag, was the ball interacting with the air. I'm calling this a contact force, but remember contact forces are actually electromagnetic forces. Okay, now let's take a look at an object that's resting on a ramp. So, some more knowledge here. Even though an object is at rest, there may still be forces exerting on the object due to other objects. For instance, this box is still interacting with the planet, so we have a gravity force. And once again, I'm working on a force diagram here. Now this box wishes to slide because it's on a ramp, and there's something preventing it from sliding. That something is friction, and the friction is right between the two surfaces. I like to use a script F for friction. This box is pushing down on the ramp, so the ramp must be pushing up on the box. So we call that a normal force. And the normal force is it's as a result of the floor pushing up on an object. I've drawn it closer to the front of the box because this box is at an angle, so it would start to try to tip up on its leading edge. So the steeper the ramp, the closer I would draw that normal force to the front of the box. If the box was on a nice horizontal surface, I'd draw the normal force right at the center. So those are really the only three forces acting on this box. So now let's make a free body diagram. So I'm going to represent this box. Now this is something that's kind of neat. This angle, or this ramp is angled at an angle, I'll call it theta. What I'm going to do is I'm going to twist my Cartesian coordinate system. I'm going to make the x-axis parallel with the surface of the ramp. And now when I go to draw my vectors, I have the normal force, which now is drawn along the positive y-axis. The friction, which is drawn along the negative x-axis. And the force due to gravity, which just is drawn straight down. So because I twisted my Cartesian coordinate system, I now have two forces along an axis. If I had not, I would have only had one force along the axis, the gravity force, and then the other two would have been off of an axis. And what's really cool is whatever your angle is of the ramp, that angle will show up right there between the negative y-axis and the gravity vector. We're going to later learn how to resolve vectors into their x and y components, so this will become important later. So, what are all the objects and their interactions? Well, the box is interacting with the Earth. So we got gravity. We have the box interacting with the ramp. Which gives us our friction. And friction is a form of a contact force, so it's an electromagnetic force. And we have the box interacting with the ramp again to make our normal force. Which once again is a form of a contact, so it's an electromagnetic. Now, an object cannot exert a force on itself. So this is a classic example. Every kid has this idea. They say, hey, if I put a fan on my cart and put up a sail, I'll provide my own breeze to bring, to make my cart work. But let's take a look at this. this fan is exerting a force on the air. So the air must be exerting a force on the fan because those two are interacting. This air then exerts a force on the sail. But this force right here on the sail is being negated by the force of the air acting on the fan. And since the fan and the sail are both connected to the cart, those forces will cancel and it'll never work. So an object cannot exert a force on itself. All right, that's going to conclude video 1.